So I'll continue a little bit with the first part about simulation, and then we'll jump to the second part about testing it in the real world or testing it on test beds. So first of all, I want to show you again a little bit our process change. I've talked about that before already. So typically, we of course have to use a lot of data. We use CityGML. This is a standard for the representation of three-dimensional city models, very advanced standard. If you don't know it, check it out. It's open source also, widely used also nowadays. Lots of satellite images or satellite data or data from planes. So for example, about elevation information, building sizes can also be scanned with LiDAR sensors nowadays from drones, from helicopters, from planes. We use it a lot. Then we use a tool which is called Roadrunner. This is nowadays our typical tool to create maps because we have decided in our institute to use OpenDrive as our standard map nowadays. So this is the basis, our ground truth for all the map information which we have. So OpenDrive being used mostly to create our simulation networks, but also to create, for example, the submicroscopic simulation based on an OpenDrive network. So this is also an open standard, mostly driven by the automotive industry for designing the surrounding of a vehicle in terms of road space, but also buildings, obstacles, trees, and so on. So quite an important standard for maps nowadays in this field. Yeah, Sumo and Unity, two tools of choice which we are using. And at the end, of course, we do the testing again, mostly at the moment in driving simulators. That's the typical process chain for our simulation studies or experiments, which we do with test persons. And you already see here, which are marked the dash lines, these interfaces, and I mentioned this before already, become very important. So we were in the past only experts in the simulation field. And for simulation, talking about microscopic simulation, that was the main, our main tool which we have used. And nowadays you see what we have to do is becoming quite diverse, lots of different diverse domains. So what we really do at the moment is majority of our work, I would say, except from the evaluation of the data, is really paying attention to these interfaces. So this is a really important thing, and we have developed also lots of our own interfaces. So for example, an interface between Sumo simulation and Unity. So sure, by the video is not working properly. Strange. Wait, let me just start it again. Yeah, I think the computer is, now it's better a little bit. Computer is quite hot. Too much videos in my presentation. So we created such interfaces for all the different tools in all the different worlds, and this is really a major task, I have to say, which is not a typical traffic engineering task. So to be able to really use the tools in real time next to each other so that there's no delays, no latencies between these tools, so that we can use that in our daily work for our experiments. We are also having interfaces between, for example, automated driving perception and driving algorithms. So for the path planning of automated vehicles based on the detection of the surrounding, and integrating this again into the visualization here in a 3D city model on the right-hand side. So you see the same situation again on both screens. This is our test vehicle, our blue bus, which Jason was already driving in. And we try to really have these interfaces between all the different tools in our world, which we are, the tool world which we are using, so to be able to use them. And these interfaces are really becoming more and more important. Here again, you see Sumo and Unity interface. I'm working for also not just cars, but also pedestrians and also bicyclists. You see here also the trajectory planning. So this is the predicted or the planned, the red dots are the planned position from the automated driving algorithm where the vehicles would like to go in the next second. So there's lots of these coupling or lots of these interfaces which are necessary to really do our daily work. Also here we see how we combine, for example, microscopic traffic simulation and 3D city models to feed the surrounding traffic, but also feed the environment into our driving simulator. Also a big step which we had to do to be able to actually perform the experiments which we want to do. So lots of preparation work is needed to be done. So let me just skip that here. That's the same actually. So typically, therefore, this is our process chain where really OpenDrive is nowadays the standard. So we use OpenDrive as 2-dimensional models, as 3-dimensional models. We use it as the surrounding, as you can see here, in driving dynamics simulation. We use it also for driving simulators, for the visualization, and we also do the data evaluation, especially the mapping, so the localization of the data in the OpenDrive format. And all of this is always accompanied by our traffic simulation, still our major tool which we use to create in 2-dimensional, 3-dimensional, and also in our simulators, creating the surrounding traffic. Let me just skip that. So I told you at the beginning, very important, what we need to do is to verify and validate our results. So typically, we have to do both steps. So verification, generally being formulated as the general question, did we build the system right? Did we build it according to the regulations? Did we build it according to the specifications which we gave it? So this is also a very important question. You don't only ask for automated vehicles, but for all the systems you design. And validation on the other side is then the step which is in research very often forgotten. That's why we luckily also have social scientists who always remind us about that this is a very important topic. So actually do the products which we engineers have designed. So we built the system right, yes, that we are good in that. We know we will do the specifications and we built the system according to the specifications. But at the end, did we build the right system? We don't know. Do the customers accept it? We don't know. I think this is also quite similar. You will probably hear this in the afternoon from Julia also. Creating a startup. Yes, you can make some nice solution for a nice problem which you have identified. But at the end, is this really a necessary problem? Is it really a necessary solution? Do the people really accept it? Do they need it? That's again the validation, so to say, of your concept of a startup. Julie will talk about this in the afternoon, yes. So these two questions you always have to evaluate also for automated vehicles. And this means when we do the verification, this we can do very often in simulation, we can do this in technical tests. This is our daily business. And then for the validation, typically we have to involve the humans. We have to bring them to our driving simulators. We have to bring them into the vehicles. We have to see how they interact with the vehicle. We have to observe it outside in real-world testing. So using real life conditions. That's very important differentiation between these two terms. Typically for validation, we also not just look at safety and efficiency, but we look, for example, at sustainability, like emissions, also look at comfort. How do people feel? Do they feel good when they use this system? Is it applicable to their needs? That's the main metrics. Yes, for verification, we have lots of different ISO standards. I'll not go into detail for them. So specifications, regulations, there exist plenty all around the world. Some are unified across different countries, some are not. So yeah. Okay, last but not least, we have lots of challenges, of course, for simulation. We talked about some of them before already. Realism being one of the main key drivers. So is it really realistic what we show, first of all, the test persons in a simulation, or what we use in a simulation? But also is the behavior, for example, which we have modeled or which we have maybe also used human behavior, is it really realistic in a simulation? That's always a big question. And therefore, again, the same sentence, all models are wrong, but some are useful. And this is, I think, a very important quote. I sadly don't know where this quote comes from. I just remember that from my lecture when I was a student back in the days. This is what our professor Fritz Busch in Munich was always saying, all models are wrong, some are useful. So keep that in mind if you do simulation. At the end, always verify and validate with the real world. That's important. Another challenge is computational requirements. You saw at the beginning, we are leaving the world of microscopic traffic simulation and going much more into the field of vehicle dynamic simulation, not just with one vehicle, but with plenty of vehicles. We use very high fidelity, three-dimensional models of the cities. Our cities become, or the test areas become bigger and bigger. We test whole cities, not just small intersections. So this requires a lot of computational power. And you see, for example, also just one news headline, Tesla has just recently invested $500 million of US dollars for a new supercomputer where they will mostly test their AI models for trajectory path planning of the vehicles. And of course, a big problem is also, especially for automated driving, scenario coverage. So I mentioned already before, we have scenarios in urban areas, in highways, and so on. But you can imagine from your daily drive on a street, there is so many scenarios in the world which you also don't learn in driving school, but you learn how to react on such scenarios. And this is something automated vehicles also have to learn. So there's different researchers stating how many miles an automated vehicle actually has to drive to really experience all the relevant scenarios on a road so that it can be considered as safe driving, if it can do that. There's numbers between 3 billion and 17 billion kilometers for testing until you can say this is a safe vehicle. So you can already see that's a lot. In comparison, I mean, the two companies which have at the moment, I would say, in automated driving mode, the most test kilometers driven, that's Waymo in US and Cruise also in US. And you see they're still far away from these values, which researchers have stated to be relevant and necessary for having safe automated driving. And I think this already shows we need simulation. And also, this is a challenge for simulation, because also in simulation, driving 17 billion kilometers, covering millions of different scenarios, that's quite a challenge. Somebody has to create these scenarios, because not all of them can be created by randomly changing some parameters. And the integration with real-world testing, that's a challenge which we have at the moment, which we are facing. So how can we really validate properly in the real world something which we have done in simulation? To create the same boundary conditions which we had in simulation, also create them in reality so that we can test the same again in the real world. So lots of challenges, most of them not being, not having a solution or proper solution at the moment. And I'll talk about this here more in the second lecture. Future trends, lots of AI and machine learning as in all the domains, I would say, so let's skip that. Lots of cloud-based simulation platforms, so it's also due to the challenge which I showed you before about computational power which we need. Lots of simulations are now being done in the cloud because of having just more GPUs and CPUs available there. We also have an increased use of digital twins, not just of 3D city models, but digital twins of cars, digital twins of everything which is participating in our traffic. So they become better, they become more detailed, and they become, which is important for us, more available. So we can also, you can find open source digital twins available. Some cities are even putting their city completely, their digital twin of the city as open source. There's lots of material available. So this is really a future trend which is already ongoing. We have enhanced realism and fidelity. So I mentioned before, we use 3D game engines nowadays a lot because they increase the realism a lot. And we have an increased use, especially in our field, of human-in-the-loop simulation, human-in-the-loop simulators. And I will show you some of the examples here. So I showed you this here already before. And we have, for example, a very nice driving simulator. Lots of projections at 200 degrees field of view. I said 190 before. We have also a Unity game engine there for the visualization. So you see also there was a crash. So there's lots of realism here in these simulations. Same for a bicycle simulator. We have also a surrounding field of view we have a helmet which we detect also with sensors. Also here, a depth camera installed so that we detect also the movement of the person on the bicycle. So we can detect, for example, this raising the arm movement as well. Also when the head is turned, also the movement of the body. So this can all be detected. Yeah, I'll skip that. That's the explanation. Yes, here you see that. So we have a skeleton model also, so that we evaluate how the cyclist is behaving on the bicycle. First of all, to evaluate, for example, if he does some safety critical movements because of a too close car or something like that. But also if he, for example, looks to the left, looks to the right, does a shoulder glance to see other vehicles. What does he see? Where does his eyes look at? So nowadays we also have cameras which are looking at the pupils, I think, of the eyes. So to track the movement of the pupils, to see the field of view also of the cyclist. So lots of technological advancements are integrated in such simulators. But at the end, as we have talked about before, I think with someone from this group here, simulations are never realistic. So therefore, to really create proper models, we always go back to reality. For example, here in Munich, to determine the behavior of the humans, may it be cyclists, may it be pedestrians, in reality, and what do they do. So we extract the data from there. Also there you see skeleton models of all the vehicles, of all the humans, sorry. So we do the same, what we do in a small scale on a bicycle simulator, also in the reality, to create a data set with the real data, how they really behave. Yes, also here you see again the movement evaluation. I'm afraid has crashed now. Yes. I'm afraid I need a Korean translation again, Jason. There's some error. Now it worked. There was an error message, okay. Pressing escape worked. So we do have the same for our cargo bike simulator. You see here now the same with virtual reality glasses. So you see on the right-hand side, the video is what this person which is driving is also seeing in front of the virtual reality. As I mentioned to somebody in the break, we had some bad experiences with using virtual reality because of vomiting of the test persons. So nowadays we use again the screens which are more safe for both the participant and us as the test supervisors. Also for wheelchairs, so we have now wheelchair simulators also there. We use similar technology to have the human in the loop, and then this time the mobility impaired human in the loop, which is very important, for example, for interactions again between such wheelchairs and automated vehicles, because maybe the sensors they overlook because they're sitting. They identify this as a different item on the road, different obstacle, not as a human. And therefore, we also integrate such simulators nowadays in our simulation framework. And last but not least, here you see the wheelchair. Last but not least, also pedestrian simulators. So also there with virtual reality glasses, having pedestrians running in an empty room where we use their interaction with, for example, cyclists, also for our studies. And we also have now very new an e-scooter simulator. So since they are really, the use is increased in German cities, I would say, we also have that model. And I brought you also a small example. Let's just check. So because we have now, I told you we have had bad examples with the virtual reality glasses, so that's why we installed something which is called a cave. A cave is a room, so to say, where we have all the ceiling, I think we have excluded, but the floor and all the four walls are actually screens. So you have a fully immersive environment around you. And you see here we can put actually a bicycle simulator, but also e-scooter simulator inside of this cave. And let me just play the video, then you see it a little bit more. So there you will see how this actually looks like. So of course, due to my video angle, it looks a little bit like moved, but you have the optimized viewing angle is from the viewpoint of the head of the driver. And this is a very fully immersive view. So the environment, it's just testing environment, it doesn't look so realistic yet, but the movement in this environment is really realistic. It feels like you're on the street. We also have the bicycle is having some vibration. We have also a fan in front of the bicycle, so they have to do the wind, the turbine. So and we have the same for the e-scooter as well. So you can easily simulate now with different simulators in this cave. This is a video which is only, I think, 3 days old. So that's why I didn't bring you the nice environment yet. This was just for testing purposes. But there's lots of possibilities, I think, with such a cave. And yeah, full stop. Okay, so conclusions. I hope I showed you a little bit the importance of testing and validation. And we talked about that and the various kinds of simulations, where we also saw several examples. Requirements. Main requirement for us is now the digital twin. That's also what we really need to set up for all of our simulation experiments. We have a strong importance of proper interfaces. So this is something where really lots of our work goes in nowadays. And the very important question at the end, which you have to ask yourself, did we build the system right? But also, did we build the right system? By answering this question, it's very important to involve humans, either by human-in-the-loop simulations, but even better by something which I will show you in the next 20 minutes, real-world testing. Yes, as I just mentioned. Okay, so let me just go to the next part. Yep. Or do you have to do something for recording? No, just start? Okay. All right. All right. So now we'll talk about the same topic. I hope it will not be boring, but in testing. So testing in the real world. That's what we do a lot now, since we realized our simulations are nice and nice to look at. It makes fun to do them. But at the end, we don't trust the results so much anymore. Especially because human behavior is so difficult to model, so difficult to simulate. And human behavior becomes every day becomes more important in our field. So therefore, we really saw the need of doing experiments. And let me just skip that agenda, because nevertheless, I will do it in 20 minutes. So it's the same, again, like for simulation. It's important for validation of the simulation results. We do it for a much more detailed safety assurance. We talked about before about safety in simulation. Not so great to evaluate in simulation, so we have to do it mostly outside in the real world. We can collect much more precise and, of course, much more realistic data in the real world. And very often also, real-world tests are a regulatory requirement to bring some vehicle in public roads. So you have to test it on a closed test circuit first to bring it on the road. That's a regulatory requirement, makes very much sense. And, of course, this also helps us to additionally improve the trust and the acceptance from our future passengers, from the consumers. That's very important. So we do lots of testing also involving, for example, stakeholder groups, like, as I shown you before, mobility impaired people, like pedestrian unions, like cyclist unions, to build public trust, also using these unions by showing them just how our research works, by implementing their requirements into our research, and by also letting them participate in our research, in our experiments, not just as observers, but also letting them, for example, participate as test persons. So, again, the same environments like in simulation, which we test, so the scenarios which we test. What we can do much more better in real-world tests is adverse conditions of the road, so meaning, for example, bumpy roads or very bad visibility of lane markings, which is important for automated driving, and also adverse weather conditions. So for example, what we have here now, sadly, on Jeju Island, rain, heavy rainfall. That's also, of course, a different obstacle for automated vehicles, for sensors especially. This is very difficult to be done in simulation because there's so many effects with maybe flooding or reflection of the road and so on, which is not so realistic to be done in simulation only. And the real interaction with pedestrians and cyclists. Since our models in our simulation for bicycles, or for cyclists and pedestrians are not yet that advanced like for cars, because there's also much more human behavior involved, it's always better to test this in real interaction because we don't have the models yet on the same stage. Key metrics, again, safety, performance, reliability, and user experience. So similar to what we have done before. We don't test so much the efficiency in real world, efficiency in terms of traffic efficiency, travel times, and so on. This is rather done in simulation, but all the other performance metrics are similar to the simulation. And we do have 2 or almost 3 different kinds of testing methods in the reality. So the first one, which I will show you also later, is what we call private testing on private grounds. So there's different names: proving grounds, private test beds, closed course testing, probably plenty of other names. What it actually means at the end is you have a certain area, fence around it, barriers, access control, and you can test there in a safe environment without having the influence of real public spaces, which is then the second kind of testing methods, where we really have people which are not participating at your experiment also being part of your experiment. So it means there's civilians walking around, other cars, they don't know that you're testing there, so you cannot control their behavior, you cannot control what they do. So it's really random behavior surrounding your testing thing, which means it's uncontrolled, it's much more difficult, and of course it's not so good to have testing of similar boundary conditions because you cannot control the boundary conditions. And the third thing, which is, I just mentioned it here, which is also kind of a testing method, is then the regulatory testing and certification, where we really have a toolbox of different scenarios which have to be tested, similar to like a driving license, which you do. There's different elements which have to be tested, and this is regulatory testing, very often done, or actually 100% being done on private testing grounds as well. So let me just give you a small example for the second part first, and then we'll go to the bigger first part. So we had a huge project in Munich, which was called Tempus, where we actually declared, I would say, 1/4 of the city as a public testing ground. So 1/4 of the whole city area is now a testing ground for automated vehicles, which means every car maker or OEM can come to Munich and test with the vehicles there. So why not in the whole city? Because in this quarter, actually, we have also the infrastructure sensors being equipped. We have our traffic signals being equipped with communication. And also for this part of the city of Munich ensures a certain quality, for example, of the road markings, so that the test vehicles can always rely on, at this area there is proper lane markings. Or at this area, for example, we inform you ahead of a construction site and tell you where it is. Why is it like that? You would say, well, it would also be good to have bad lane markings for testing. True. Then they can go to other parts. But for testing with perfect conditions, that's exactly the area where the vehicles should go to. And where it's also easier to get the permission to test. So it's very simple from the bureaucratic process, or not very simple, but in German terms, very simple for German bureaucracy to get permission to test on these public roads. There's also for the marked roads which we have here, I mean, there's also lots of urban roads here in between, which are not guaranteed that, for example, if there's a construction site, it's in the system. But all the yellow roads and all the other colors which you see here, this is really the major roads where all the information is given, and also where a full HD map is available from the city of Munich. It's like open source if you register, and you can download for your car, for example, for preparing it offline in a simulation, already this HD map for this whole segment. There's also lots of freeways involved, so you can test on all different categories of road in the real world. So this was quite a big step to allow that. And of course, we have lots of challenges. I mean, I told you already, real-world testing is really at the end of the complexity level. It requires the most effort, time, money, and motivation to really do that. So lots of regulatory and legal hurdles, typical. So you need to fulfill ethical requirements. You need to talk to the ethical boards of the city, of the state, of the municipality, of the country. They all have to look through that. Lots of data privacy issues with the cameras. So lots of legal and bureaucratic hurdles which you have to cope. Safety and liability concerns. It's still not 100%, I think, legally defined who is liable in case an automated vehicle has an accident. Is it the programmer of the algorithm? Is it the car maker? Is it maybe the city which has provided additional information from sensors at infrastructure and they were wrong? Are they liable then? So is the passenger in the car liable because he didn't push the emergency brake button? So it's still not 100% cleared. Also for vehicle operation, for test vehicle operation at the moment, of course, it's the testing company which is liable mostly, but yeah, it's still an issue. And we have, of course, high investment costs, high resource requirements. You need lots of personnel to do that. You need the vehicles, of course, and producing such a vehicle, you can imagine, is even more important and more expensive than just creating a simulation. And we have the variability, so it's mostly for demonstrating that your car or your vehicle can operate in variable conditions. It's not so good for developing purposes because you cannot rearrange the situation around your car in the same way to test it once again. So due to lots of human involvement in this testing in real world, it's quite complicated. That's why we typically do experimental digital twins and experimental twins. That's two terms which I will just briefly explain you. So typically experimental digital twin, this is something which I've shown you before. So we have again the combination of the different simulation worlds, and we use real-time traffic data to simulate the real copy, so to say, a real twin of the current existing reality. And we do then the testing and validation with real data. So typically what we do, real data from our simulators, but also from our test track, which I will show you later. So we created an experiment test track, a test track for experiments, where we can really test things which we cannot do in simulation in a real environment. So this was what I have shown you in the first lecture, also the simulators. And for the second part, we will talk about the experimental twin, which will then also include like real world data and testing on real roads, but on real private roads. And for this, we have built something which we call the Future Mobility Campus. So this is a test track which our institute, actually my research group, has built. It's also in the city of Munich, or south of the city of Munich. And we do have several testing facilities there. So on the left, on the top, you see a parking garage where we have automated valet parking. We have automated charging there with inductive charging, but also robot charging, where the vehicles can test different things. We have a park and charge lane where vehicles, like in a taxi buffer at the airport, just enter the lane automated and are charged while they continuously move forward to the end of the buffer. We also have a simulation center nearby where our driving simulator, for example, is standing at the moment, where we can couple, for example, the real world testing with simulators. So for safety critical situations, we can still do we can still do simulator tests. So having two vehicles crashing into each other, but only one is a real vehicle and the other one is a simulated vehicle. I'll show that later. And we have completely variable testbed design. So all what you see here on this gray area, this is just tape. So we put tape as lane markings there. We can move the traffic signals. They're like construction site traffic signals. Everything is movable, adjustable, and we have full connectivity there with 5G network, on our own 5G network, and our own V2X communication network. So this is like a playground for us researchers where we can do lots of experiments together with the company IABG and the Bavarian Ministry of Transport. And let me just skip that. I'll just show you some images there. It's not under operation yet. This week we have finished our construction. I think within the next year I can show you much more real images from there. At the moment it's only from our designer. So just to give you an overview about the different areas which we have here. So our parking garage. We have also inductive charging while driving. So there's inductive charging technology in the track, and we can drive over that. Automated shuttles, and so on. So let me just go then to the next one here. Yes. Oh, that was too fast. So, and we use that testbed a lot for the certification of automated driving algorithms. So we have developed also our own algorithms. We test also with partners or for partners. And for our own algorithms, we have also created now our own automated driving car, which we called Edgar, which is just a big bus with lots of technology on it. But also we have our automated rickshaw, which actually my team has developed. It's a 3-wheeled, lightweight vehicle with LiDAR sensors, radar sensors, and cameras. Driving automated, it can carry 2 passengers as well. Limited to 20 kilometers at the moment. I would say the 25 are just a little bit too much at the moment for us still, because the LiDAR sensors cannot look that far ahead. And we actually use that to test already automated driving algorithms in a vehicle which is not so easy to destroy also, which is not so fast. And we also use it for student projects. So whenever you think about doing a PhD or a postdoc in Munich, you can probably also use student groups to develop some algorithms or test some functionalities. We're now building a second and a third rickshaw as well to test car following models and so on, and overtaking. Yes. And let me just go there. We also have some other vehicles which we're testing there. So since you saw the test track is small, it's just 100 to 120 meters approximately. We are now also building such scaled vehicles, 1 to 10, so small cars. They're like this big, with the same functionality. So they also have a small LiDAR sensor on the top. They have cameras, they have video sensors. They also have V2X communication. So with them, we can just use a smaller tape on our test ground and make smaller roads on our test ground, and then drive on like 1 to 10 scaled environments. Why do we do that? Not just because of space constraints, but also these vehicles, we produce them for much cheaper price than the real big automated vehicles. So therefore we can test with much more vehicles the interaction between 10, 20, 30 automated vehicles, maybe at an intersection or in a freeway traffic and so on. So this is the big benefit. We have very highly equipped highly equipped connected bicycles. So this is a Boreal bike which we have bought recently. Also LiDAR sensors on board. So we use that, for example, for detecting pedestrians and sending this information to the traffic signal so that we can have a green wave for pedestrians. And we have the same also for our e-scooter, which also has lots of sensors and which we use for such testing. So second last slide, and then we finally can have lunch break. Sorry for my long lecture today. Future trends. So again, just like in simulation, we have lots of AI and machine learning coming into our field. We have the increased integration of behavior models. So this is something which research all around the world is developing very rapidly now. Behavior models for cyclists and behavior models for pedestrians. Why do we need them? Not only for simulation, but mostly for automated vehicles for predicting the behavior of them. So if an automated vehicle drives on the road, it would be great if the vehicle could predict from the surrounding pedestrians and cyclists what they will do in the next seconds. The same what you as humans do. We also predict their behavior from our own experience. And vehicles have to do the same to be able to do a safe maneuver between pedestrians on the road or cyclists on the road. We have a lot of integration of smart city infrastructure, so the cities become highly equipped with sensors, highly equipped with connectivity. Lots of traffic signals nowadays send their status to the vehicles which can receive that. We have lots of ongoing advancements in the field of sensor technology, so not just because they become cheaper and more affordable, but also because the range becomes higher. The algorithms which we use to detect objects from sensor data becomes much more advanced. And we have lots of various advanced hybrid testing methods, and that's the last thing which I will show you today. Something which we did not completely do yet, it's only a concept. And our concept involves something which we do in simulators. We equip test persons with VR or AR glasses, but we let them drive on a real vehicle on our real test track. So why do we do that? Because we give them in their field of view an error has occurred in the recorder. Not enough disk space to write. Should I just ignore it?
Yeah.
Okay. Okay, so because we can use the AR glasses to bring a virtual environment additionally to the existing environment into the field of view of the test person, which means we can do safety critical testing regarding the ethical standards, of course. This is still something we have to do. But you can, for example, have a crash between a real vehicle and a virtual bicycle on the road, or in a very safety critical situation between the two of them, without endangering any one of them, except maybe ethically so on, but this is something we still have to do. But you can bring a virtual environment additionally to the existing environment into the field of view of the driver and do testing between our simulation world and our real world. So we have maybe even a bicycle driver on our bicycle simulator and bring him into the field of view of the driver of the real vehicle. Okay? So of course, we do this only in the boundaries in our test intersection, and also the virtual world has to end, or the real world ends, so that our driver doesn't drive in the fence. But this is something which we are currently we are developing it and doing that to test better in the future. So, recorders here. Okay. So this is what we call augmented reality co-simulation, bringing reality and virtuality together and mixing these two worlds. That's why also our simulators are very close by. That's due to latency issues. So we have to reduce the latency between our real world and the simulated world. That's why they're close by. And this is something which we do right now and bring all these worlds which I have shown you, bring them together into one experimental twin, as we call it, where we can really test all our simulators together with microscopic simulation and combine this with real-world testing as well, where we can have not just safety critical tests, but also tests of where we have more realistic behavior of the vehicle, because it's a real vehicle, and more realistic behavior of the human in the vehicle driving, because it's a real driver of a vehicle. So it has not the flaws of the simulation anymore, or the flaws of the bias of simulators. And that makes it quite nice. Okay, that would be the end of my lecture for today. We have plenty of time for questions, I think the whole day. So if you want to go for lunch right now, I guess we should...
Well, just 5 minutes.
Okay, 5 minutes of questions, and I'll be here for the whole day. And then you can ask them later as well, because
yeah,
it's
5
better
minutes.
to ask them when you're not hungry.
Yeah, 5 minutes, first come, first serve, so...
Okay, I have 5 questions written down,
okay.
But I'm not going to ask all 5.
I give you 2.
Okay, 2's good, because that's the number I had in mind. The first one, thank you so much. The first question I want to ask you is whether you've compared the findings between the simulators and test beds and whether you find any similarities, because that would really prove the robustness of the simulators. My second question is that in 2021, I'm sure you know the KPMG produced the AV readiness report,
yeah.
and Germany was surprisingly quite low. I thought it'd be like the first or second, but it was like the ninth or something.
It's all bureaucracy.
Oh, really?
I'm afraid, yes.
Really? Because I thought it was a variation between different areas in Germany.
But I think we made very few points in bureaucracy, so legal requirements and so on. So Munich did a good job now.
Right,
so they
exactly.
did that, but it was quite a tough work.
Okay. Yeah, so those are my two questions. I think the second one you've already answered.
Did we get a hint for the first question?
Any similarities between the
Yes.
findings of simulation?
Yes.
Testing?
I didn't have so much time because I was talking too long for the first part. But this was one of the main reasons why we did this experimental test track. Because we realized our simulations for automated vehicles, we assumed some models for how the automated vehicles drive. Of course, we assumed some models for pedestrians and cyclists, and we realized that's quite different to what we observed with our drone data when we did the real public road tests. Why is it so different? Our models are not good, our environment is not good, something is not right. And I mean, this is something which we have in lots of different domains. We always have the example from medical domain. So you do some computation about how the medics would work in a simulation maybe, or in some theory, but at the end you bring it to the market and then the patients react completely different. So what do they do in between? They do controlled experiments. And we thought, why we don't have this in traffic engineering? Why is it like that? We need that. And that's the reason why we built this test track, to be able to test, without going to the market directly, test these simulation and models in a more realistic environment by combining them. That was exactly the reason why we built that. So the answer is no. It was quite different between our simulation results and the real world. So that's why we needed something in between to validate where is the problem exactly and to close this gap.
Thank you.
Please. Okay, thank you. My question is, how could you guarantee you can generalize your result to the all over the world? Because if you just use localized people to engage in your experiments, always be criticized, because different people in different local or context will have different behavior or background, cultural or behavior or attitude. So that's my question.
Absolutely. Yeah, that's a very good question. So we call this traffic culture. I think that's what you're referring to. For example, if you would do the same thing here in Korea, they would get different results than Germany because the behavior is different. Did I understand this correctly? Okay. Yes. That's absolutely true. I mean, that's why typically we are a little bit racist in our simulator experiments, because we very often say you have to have a European driving license, because we don't want lots of Chinese, Indian, Indonesian people who have different traffic cultures, because they would bias our results. I hope that this is recorded, right? Okay. No, I mean, yes, you're completely right. In different countries, you have different traffic cultures. So, for example, here everything's quite organized, everybody's driving quite defensive. If you go to, I don't know, in Italy, even the people in Italy, they drive much more offensive than we drive in Germany. That's just the behavior. Everybody's used to that. It's not more dangerous. Everybody's used to that. I think I also experienced here a difference between Seoul, where the vehicles are stopping in front of the zebra crossing. Here in Jeju, they don't really stop. So if you do a step on the zebra crossing, yes, they do stop. So there is definitely a difference. And at the moment, we do not generalize our results. So we make it exclusive and say, well, please, now we only need German test participants, or at least participants who were driving in Germany for at least 5 years, 50,000 kilometers for this one, something like that. We do that not because we're racist, but because we need to limit our data to similar traffic culture or similar traffic behavior. We can open up later. At the moment, we didn't do that, I have to tell you. But of course, this will create different results. And so therefore, at the moment, we can only generalize, I think, our results maybe for Munich, maybe for other German cities, maybe for other European countries, but definitely not for, I don't know, traffic behavior in, I don't know, somewhere in India. That's completely different. So this is a step which we still have to take, but we didn't do it, to be honest.
Thank you so much.
Okay, the next question. Okay, go ahead.
On the simulation at the microscale and macroscale, what are the evaluation of this for each simulation?
For micro and macroscope. Yes. So typically in microscopic you look at more at the vehicle level, and from macroscopic you look at traffic streams. So typically, for example, if you want to consider safety evaluations, that's not possible in macroscopic simulation. That's only possible in microscopic or maybe even in submicroscopic simulation. Macroscopic typically only looks at efficiency. That's the main difference there.
Okay, any other questions? Maybe hungry? And then Q&A session for all day?
Yes.
All day.
As long as I can talk at least.
Okay, well, enjoy lunch, and we're gonna back at 2 p.m. and with the Julia's presentation. But before that, if you have questions about the simulation and test build, Martin is here, so there will be plenty of chance. Okay, so thank you very much.